Hey, in this video, I wanted to give a quick introduction to acids and bases. Hopefully, you've heard of the terms acids, and bases before. It would make sense that we started this off with just a quick definition of what an acid or a base is. And it can be a little bit complicated because whether or not something is an acid or a base has to do with the role that it plays in a chemical reaction. All right. So just as a quick analogy to this, if I were just show a football player standing all by themselves, let's pretend this is Tom Brady, and I were to say, is this person offense or defense? Well, you might be inclined to say offense because Tom Brady's a quarterback. All right, but it's not that easy because there are situations in which this player could be playing defense. All right, for example, after an interception, the role that Tom Brady would be playing would be defense. All right, so the thing about an individual football player is you can't tell whether they're offense or defense until you see exactly what they're doing in a play. If they're trying to prevent scoring, they're defense. If they're trying to cause a score to happen, then they're offense. All right. Same thing happens with acids and bases. All right. You could take the exact same chemical and in a certain situation, behaving in a certain way, it would be acting as an acid. And in a different situation, behaving in a different way, it would be acting as a base. All right. So we're going to have to actually see what it's doing in a chemical reaction to be able to really identify it as an acid or a base. All right. And we'll show what those rules are in just a second. All right. Second thing that makes these definitions a little bit difficult is that there are actually multiple sets of definitions. All right. As history has gone on, we started off with one understanding of acids and bases, and as time has gone on, our understanding of exactly what it means to be an acid or a base has changed. All right. And so there are some very practical definitions, and then there are more technical definitions of what it means to be an acid or a base. All right. So just as an obvious, analogy to this, if I were just to say, how do you tell if somebody's old? All right. Well, if you look at a crowd of people, you can generally identify, someone who is elderly versus someone who's, in their a teenager versus a really young child. All right. But the thing is, what do you use to make those judgments? All right. You generally use some obvious cues, hair color, skin texture, maybe the sound of their voice. All right. But is that technically what makes them old? All right. No. When it comes down to technically what makes them old, it's their birthday. All right. So here's the thing. If you wanted to get it accurate, which definition would you use? The practical or the technical? All right. We would have to use the technical. All right. But what do we use more often? All right. Well, we generally make those judgments using more obvious cues about a material. Same thing happens with acids and bases. There are really quick ways to spot acids and bases, but sometimes you can get things wrong if you're only using these quick, simple ways. And there's some more technically correct ways to do it that are kind of impractical, but they always get the answer right. All right. So first of all, the acids and bases have kind of had an evolving definition throughout the years. All right. A long time ago, people identified acids more by what were some things that you could perceive about them. All right. We knew that acids were things that tasted sour, and we know that they're the way that they behave, they could corrode metals. Specifically, they would give off hydrogen gas when they reacted with metals. And bases were things that tasted bitter, and you could tell that something was a base because it would have a slippery feel between your fingers. All right. But the thing is, this is more or less describing how how your senses would perceive them. All right. But it doesn't really say what they are chemically. All right. By the way, I do want to mention that even though these are some of the historical ways people identified acids and bases, that taste is no longer really considered a safe way to identify chemicals. But if you've ever tasted lemon juice or vinegar, which are acids, you probably are familiar with that sour taste that some acids have. So on a more chemical level, there's actually two sets of definitions that you're going to be responsible for understanding about acids and bases. All right. There's actually a third set of definitions, which we're not going to get to in this class. All right, so the first set of definitions is the Arrhenius set of definitions. All right, and the reason I say set is because there's a base version and there's an acid version. All right, so this Swedish chemist named his last name was Arrhenius. He came up with a set of definitions for acids and bases. He said that an acid was a hydrogen-containing compound that generates either H+, which we call a hydrogen ion, or H3O+, which is a hydronium ion, whenever you dissolve that in water. All right. His definition for a base was that it was a hydroxide-containing compound that generates OH-, which is hydroxide, when you dissolve it in water. All right. So according to this definition, all right, so he mentioned that either of these things right here, if produced, would indicate that the material was an acid. All right, so if we took HCl and we dissolved it in water, you're going to generate, and this is actually not entirely true, but we'll just say this for right now, H+ ion, which is dissolved in water, that's why we say aqueous, plus Cl-. All right, and by this, when you see this chemical behaving in this way, dissolved in water, and it generates H+, that was enough to identify it as being an acid. All right. The thing is, this, as time went on, we realized that this did not actually happen. And I'll say a little bit more about that in a second. More accurately, what happens is that HCl reacts with water, and essentially what's going to happen is this HCl is going to give the water this H, essentially an H+, all right? And when that happens, it makes H3O+, which we call hydronium ion, plus Cl-, all right? So notice that in either one of these reactions right here, you can see that water is acting as an acid by the Arrhenius definition, all right? The base definition is a little bit simpler. Take something like sodium hydroxide. This is a hydroxide-containing compound, and when you dissolve it in water, it generates hydroxide ion. All right, so that's what makes it an Arrhenius base. All right, so I mentioned before that this is actually the more accurate thing that happened. All right, between these two reactions right here, and the reason for that is that there's actually no such thing as free dissolved H+ ion in water. All right. People used to think that you could have free H+ in water in the same way that you can have free sodium ion. Like, so if you dissolve salt in water, you're going to have some free swimming sodium ion. All right, and people used to think that in that same way you could have free swimming just H+. All right, as if hydrogen, as this was the positive ion of a hydrogen atom. All right, we later figured out this thing right here, H+ doesn't really exist as a separate ion in water. But instead what happens is H+, if it's ever near a water molecule, would essentially be bound to one of those bound to one of those water molecules. All right, so if you were to have a free H+, which we really don't have, but if it were to exist and it were to be near a water molecule, that water molecule would instantaneously grab onto that H+. All right, and if you can see, picture this lone pair right here making a covalent bond with that hydrogen right there. All right, that would create this bond right here. That's why we have two lone pairs on this water molecule, but we only have one lone pair on this one, because that second lone pair provides the electrons that are making this bond right here. All right, that actually puts a plus charge onto that oxygen atom. All right, and that's what they mean by H3O+. All right, that is what's called hydronium ion. All right, so one quick way to think about what H3O+ is that it's essentially a water molecule that's got an H+ stuck to it. All right, and we'll talk a little bit more about that in a second. So the one thing about that, about hydronium ion, if you think of it as a water molecule that has an H plus stuck to it. Well, essentially, it can transfer that H plus to other water molecules. All right, and so the reality is that an H3O plus ion doesn't really stick around for very long. They are very short-lived. All right, and so one way that you can think about it is to think about the H plus kind of like a hot potato. All right, if you've ever played the game Hot Potato, where one person, you're in a group and you kind of like one person's holding it at a time, but they always throw it to somebody else, and then they hold it for a second, then they throw it to somebody else, and then they throw it to somebody else. It kind of works the same way, where you've got this H plus, which is going to be stuck to a water molecule, but it can give it to a neighbor, and it does this very quickly. All right, so this neighboring water molecule can actually grab, let's pretend it's going to grab this. So there's a hydrogen right there. All right, well, the electron pair on this oxygen right here can essentially make a bond with this hydrogen, and the electrons in this bond right here essentially go back onto this oxygen right here. That's why we now have two lone pairs here. All right, but now we've only got one lone pair on this oxygen right here. And where did that other lone pair go? Well, that is now the pair of electrons, which is making up this covalent bond. All right, so essentially what's happened when this has occurred is that this hydronium ion has transferred an H plus to this water molecule. All right, but notice there was never a point in time when the H plus existed by itself. All right, it went straight from this molecule to this molecule. All right, and that's why we technically don't really view this right here as happening. The H plus has always got to be associated with the water molecule, and when it's temporarily stuck to that water molecule, it's H3O plus. All right, so as time went on, people realized that there were more ways for things to be, more general ways for things to be an acid or a base that weren't technically described by the Arrhenius definition. And so that's when these two chemists, Bronsted and Lowry, came up with their definition of acids and bases. And in their definition, an acid was a hydrogen ion donator, and that a base was a hydrogen ion acceptor. All right. So, and the thing about this is that these things always work in tandem. If you have something in a reaction acting as an acid, you have something acting as a base. All right. It's kind of a little bit like saying a buyer and a seller. If you see a transaction where there's a buyer, well, the thing that it's interacting with has got to be a seller. All right. So take a look at this reaction right here. All right. So what we have, we've got these two things, and you'll notice, well, if you take a look at this thing becoming this thing, all right, notice that essentially this water molecule has lost an H plus. All right. Notice that this hydrogen is no longer there. It's just got essentially this part of it right here. All right. And when that happens, that's when it gains that third electron pair. That third electron pair are the electrons that were in this bond right here. All right, that makes O minus. And notice that this one right here, where did that H plus go? Essentially, this electron pair on this molecule grabbed that H plus. All right, so that's why the electron pair is no longer there. The electrons are now the electrons in this bond right here, and it's got an extra hydrogen. All right, so if you take a look at the roles here, this thing is essentially accepting an H plus from this water molecule. All right, and because of that role that it's playing in this reaction, this is a thing being a donator of an H plus. Well, that means it's acting as an acid in this reaction. All right, which sounds a little bit weird to hear that water is an acid. All right, water can sometimes act as an acid. It can sometimes act as a base. All right, and just in this particular reaction, it's acting as an acid. Well, if it's acting as an acid, the thing that's it's interacting with has got to be acting as a base. And the reason that it's acting as a base is it is accepting an H plus. All right. So one thing about these types of reactions, notice that if you drew these as the formulas, which is what I've done right there, the total charge on this side is 0. But if you added up the total charge between these, well, a positive 1 and a negative 1 is 0. The total charge is the same on both sides. All right.